This video is on key features of exponential functions. First, recall the parent equation for an exponential function, y equals a times r to the power of x. Remember that any letters could be used in place of a and r, but these are commonly used, where a, the number in front of a base raised to an exponent, is the initial value, or the y-intercept. And r is the growth or decay factor. This is a total in parentheses. Remember that when we looked at specifically growth and decay applications, the growth or decay rate is that number's difference from 1. Let's start by looking at a graph that is already done for you and talking about the same key features that we talked about when we looked at linear key features. When you look at an exponential function, one of the important things to remember is that in this case we're looking at a growth function. Notice that this function is increasing. As x increases, y also increases. And so we have an increasing function, or growth. The domain is going to be all possible values of x. And so when we look, we always start at the furthest to the left that we possibly can, and we see an arrow. And so I know that the domain starts at negative infinity. Now, as I go to the right, you might think that, yes, the arrow keeps going up, but I don't want you to be fooled into thinking that it stops at 4, that it's going to have an asymptote this way. The asymptote for an exponential function is always a horizontal line where the function sort of bottoms out, where the y value has a lower limit or an upper limit. The domain, as long as there are arrows at both ends, the domain is from negative infinity to positive infinity. And if you recall, we show it in interval notation. Negative is always on the left, positive is always on the right, and there are round brackets for infinities. Now the range is different because the range is all possible y values. An important part of seeing a graph of an exponential function is understanding asymptotes. This exponential function has an asymptote right on the x-axis. It is sort of an invisible line that this graph approaches but never reaches. And if you looked at a table, which we'll do in a few minutes, it might be more clear because you'll see that as x gets smaller, y approaches 0, but never actually touches 0. For instance, the point -1, maybe 1/2 for this point right here. And this might be -2.25. And these numbers are going to get smaller, and it looks like the graph of the curve touches the x-axis. It is your job to understand that an exponential function approaches some line, often the x-axis, but not always, but never actually reaches it. And that is called an asymptote. And so our range, our possible y values, start at 0, but don't include 0. And so I'm going to use a round bracket. I would use a square bracket if I was including the number 0. And if I work my way up the y-axis, there is an arrow. It keeps on going up, and so that's to positive infinity. This exponential function we already decided was increasing, and it's always increasing. We start on the left and we're always going uphill. It's true that we're going uphill faster at some points than others, or it's steeper the farther we go along this curve, but it is definitely always increasing. So from negative infinity to positive infinity. For end behavior, you remember as x approaches positive infinity, as x goes to the right, y is also increasing. So as x goes to infinity, y also goes to infinity. And then we work that backwards as x approaches negative infinity. So as we're moving to the left, what happens to y? We talked about it a few minutes ago. My y values get lower, but what do they not ever go past? Y is approaching 0. It doesn't ever reach it, but it approaches 0 in this case. The x-intercept is where the graph touches or crosses the x-axis. Does this? I hope you said no. Remember, the asymptote is not part of the actual curve. It is this invisible line that the curve approaches but never reaches. It is not part of the graph. The y-intercept in this case looks like the point 0, 1. That would be this point right here. The asymptote can be described giving the equation of that invisible line, and we often draw them in with a dashed line to help us focus on them. A horizontal line, if you remember, always has an equation that looks like y is equal to some number. And in this case, y is equal to 0 at every point on this red dashed line. X is lots of things, but y is always 0. And so if your asymptote was up here, your equation would be y is equal to 4. And if your asymptote was down here, your equation would be y is equal to negative 2. Extrema is max and min, and there is no top or bottom to this. And so there is none in this case. All right, let's look at an applied problem, which is most likely how you will answer these. In this case, we have a table given to us, not a graph, and they give us the scenario. A pendulum is swinging to 90% of its height on each swing, and it starts at a height of 80 centimeters. So first you need to decide if this is exponential, which it is because we're talking about the rate of change being a percent, not a constant number, but each time it's going to be a percent. So is this exponential growth or exponential decay? And if you look at your y column and you see your numbers going down, that's a clear indication that we have decay. And if you think about a pendulum swinging, doesn't it, you push it once and then it swings less and less each time as it's sort of the force diminishes? And so think about what's happening in real terms. All right, so we have a decay equation, and we can write it using our initial value, which they tell us is 80, and it's also our first one there. And we have 90% of its height, and so we're going to use 0.9 because we always change a percent to a decimal to the power of x. So we've decided that this is exponential. The domain in this case, in this applied problem, you have to think about all possible values here. So yes, I can have 0 swings, I can have 1 swing, I could have 100 swings, but I definitely can't have a negative number of swings. So in this, my domain is going to be from 0 with a square bracket, whoops, to positive infinity. We don't actually know when the pendulum stops, is completely still. For the range, I'll put it on this side, you're looking for all possible values of y. Well, at some point it's going to stop, so our height technically would be 0. And so our range would start at 0. Negatives don't make sense since we're talking about height. Square bracket, because at some point it will actually stop, have no height. And the highest, where it starts, is 80. And so our range is in interval notation from 0 to 80. Now, a lot of these are going to be easier to look at on a graph. And so, For part of your assignment, I'd like you to actually graph this and look at it and see what you can come up with to finish the rest of the key features for this graph. The following is a summary. We have key features of exponential functions. They mean the same thing as for linear functions. Really, the only difference is that with exponentials, we have an asymptote. An asymptote is the invisible horizontal line that the exponential function approaches but never touches. It's often just below the graph, but of course if we flip that graph over, it's possible that the asymptote would be just above the graph, as we'll see tomorrow. The table feature on your calculator is going to be really convenient to find the asymptote, and we'll do that together because it's not going to be clear just looking at the graph in many cases. The equation of an asymptote that's a horizontal line is always in the form y equals whatever number that line passes through on the y-axis. The range of an exponential function begins at the asymptote if it's a growth equation, and it never ends. And this can be different when it's an applied problem, but in a general graph this will be the case. The domain, also on a general graph, not in an applied problem, is also going to be negative infinity to positive infinity, just like a linear function. Unless there aren't arrows on the ends, it keeps going.